everyone, and welcome to the series on probability theory. And today we're going to be talking about one of the more important theorems associated to probability theory, and that is the change of variables relation, both for one variable and multiple. So let's assume that x is a random variable with probability density f of x, and let's assume that y is some transformation on that random variable. Let's call it g. Typically, g is monotonic, but even if a g is not monotonic, we can still work around that. So if you transform the variable x and turn it into y, what is the probability density function for your new variable? So let's see if we can derive this very important relation. So let's suppose that y is equal to g of x with g invertible. That means x will be equal to g inverse of y, right? And let's, of course, mention this very important note. So it's easier if g is 1 to 1, and if it's not, partition the domain of x into mutually exclusive domains, let's call it sk, such that g is 1 to 1 on each of the sk's. Right, so that's very important. So let's assume that our function is monotonic on a particular domain, and then we can derive the change of variables formula on that. All right. So of course, let's suppose that fy of y, that's the cumulative density function for y, is the probability that y is less than or equal to y. Right? In case you don't remember this is the CDF of random variable y, commonly defined as the integral from minus infinity to y of fy of t dt. So one very important relation that you should know about the probability density function and its derivative, the derivative of the cumulative density function will always be equal to the probability density function of that random variable. And you should be able to prove that using the fundamental theorem of calculus. So if that is the case, then what do we know? So capital F of y, by definition, is the probability that y is less than or equal to y. But y has a new name. Y equals g of x. So we can write this instead as the probability that g of x is less than or equal to y. And then we can invert this on both sides inside of the probability statement. So this is going to be equal to x is less than or equal to g inverse of y. And that's a probability statement about the random variable of x. So this is precisely equal to the cumulative density function for x evaluated at the number g inverse of y. So we have that fyy equals fx g inverse y. So if we differentiate both sides of this expression with respect to y, we're going to have ddy of fyy will be equal to, of course, fyy, and that's going to be equal to the derivative with respect to y of fx of g inverse of y. And then what do we have? So this is going to be a composition of functions. So the derivative of the outside, so that's going to be fx. That's going to be its marginal function, little f of x, which is known, evaluated at the interior. And then we need to multiply by the derivative of the inside, which is a function of y, of course. Right? So we have that fyy, the density of which we want, can be expressed in terms of this expression. Now, if g is monotonically decreasing, then this needs to be an absolute value placed around its derivative. So therefore, we have this very, very important relation. Fyy will be equal to fx evaluated at g inverse of y times the absolute value of the derivative with respect to y of g inverse of y. And that's what we refer to as the change of variable theorem for one variable transformations. Now that we have derived it, let's work through an example to demonstrate its use. as our example, let us assume we take x to be an exponential lambda random variable whose density is lambda e minus lambda x for x greater than or equal to 0 and 0 otherwise. And then let us define y to be equal to x squared. So it's a transformation on that exponential, so it's technically the square of an exponential. What will the distribution of the square of an exponential be equal to? And you might want to pause the video and see if you can try this on your own. So let's begin. So our transformation on our variable x is going to be g of x is equal to x squared. So if we invert this, g inverse of x will be equal to the square root of x positive, because obviously x is greater than or equal to 0, so this is going to be the positive one. So therefore, g inverse evaluated at y will be equal to the square root of y. And this is going to be what we're going to be using to evaluate into our density and also to differentiate. So if we take the derivative of this expression with respect to y, so the derivative with respect to y of this expression, that's going to be equal to the derivative with respect to y of the square root of y. Keep in mind, that's y to the power of 1/2. 1/2's going to come down. Power is going to be negative 1/2 by the power rule. And we can write that in simplified form as 1/2 square root of y. So using our change of variable relation, what do we have? So the density function for y evaluated at little y will be equal to fx evaluated at g inverse of y, which is going to be that relation again, times the derivative of our inverse with respect to y, absolute value. Now keep in mind that's always greater than 0, so we need not worry about the absolute values. So this is going to be equal to what? So lambda e to the minus lambda x, and x is now equal to the square root of y, times 1/2 square root of y. So let's just rearrange this just to make it a little bit nice. We can write this as lambda divided by 2 times y to the minus 1/2 times e to the minus lambda square root of y, and that's going to be defined for y greater than 0. So that is our probability density function for y. So one interesting question, is this really a probability density function? You should be able to quickly verify that this is always non-negative, so that's not an issue. But let's see if we can find the integral and see if it's still equal to 1. So the integral from 0 to infinity of our new, hopefully, density function, y to the minus 1/2, e to the minus lambda, square root of y, dy. What I'm going to do is I'm going to use a u substitution. Y is equal to u squared. So dy will be equal to 2u du, and you should be able to see that the limits, 0 and infinity, are not going to change here. So this is going to be equal to lambda over 2 times the integral from 0 to infinity. Y is equal to u squared, so it's going to be u to the power of minus 1, and then e to the minus lambda, and the square root of u squared will just be equal to u, positive side only, and then we're going to have 2u du. Our 2 is going to cancel, u minus 1 and u will cancel, and then we're just going to be left with lambda times, or actually, let's write it, the integral from 0 to infinity of lambda e to the minus lambda u du. And who is that? Well, that's just an exponential probability density function for random variable u. And since that's a PDF, that integral is equal to 1. Or we can verify using integration by parts, and that would be pretty nice as well. So therefore, it is indeed a probability density function, and you should be able to verify that it should give you the same exact results. So for example, y is equal to x squared. So if somebody asks you what is the probability that x is bigger than 2, then that should be equal to the probability. So if I square x, or square both sides of this, and keep in mind that's with respect to x, then that should be equal to the probability that x squared is greater than or equal to 4. And keep in mind, what distribution is that? Well, that's still x, but y is x squared. Therefore, this can be done for the probability of y, that y is greater than or equal to 4. Generally speaking, you should be able to verify that for any a value, and that will indeed still be satisfied. Another little exercise that I'll leave for you for this particular example is to show that the expected value of y will be equal to 2 lambda for this particular probability density function. Now let's see if we can generalize this. Now let's assume that x and y are random variables with joint probability density function given by fx y. let's assume that G is equal to a transformation on both of them. What is the probability density for Z? So obviously we're going to be using some multivariable calculus relations here that you should have been able to build before, in particular the Jacobian matrix. So let's see if you remember that right now. So let's assume we have variables u and v. So these are going to be the variables that we're going to be going to. For example, in Calculus 3, you probably remember that we commonly converted from rectangular to polar coordinates. So that is, we sent xy to r theta. So here, uv will be equal to some transformation on our original variables x and y. And if this is true, that means our original coordinates will be equal to the inverse transformation on our new coordinates. Right? So here we have some transformation, and since that is a transformation on coordinates, then that transformation should have a Jacobian associated to it. Remember that the Jacobian for this inverse transformation G inverse will be equal to the matrix of all first order partial derivatives. In particular, we're going to have the partial derivative of x with respect to u, and then the partial derivative of x with respect to v, and then the partial derivative of y with respect to u, and the partial derivative of y with respect to v. And that's going to be our Jacobian matrix for that transformation G inverse. And then the determinant of that Jacobian will be equal to what? So that's going to be equal to AD minus BC, so partial x, partial u, times partial y, partial v, minus partial x, partial v, times partial y, partial u. And that would be the Jacobian for that particular matrix. And the important theorem that connects these things together is as follows. The probability density function for uv, evaluated at uv, will be equal to fxy, evaluated at xy, times the absolute value of the determinant of the Jacobian matrix of G inverse, where G inverse connects these coordinates xy with uv. In case you do not already know how to prove this using multivariable calculus, I highly suggest you work on that because that's very, very important. Because that's pretty much why we can convert, for example, the integral of fxy dx dy into the double integral of f r theta r dr d theta, because here dx and r dr d theta are going to be the connections with this Jacobian matrix. So r dr d theta is the determinant of the inverse between x, y, and r theta. So if I want to extend this to multiple variables, can I easily do that? Hopefully the answer is yes. So generally speaking, we can have the following. Let's assume that we have new coordinates, u1, u2, down to um, and obviously that's going to be an element of n-dimensional R space. And we also have x, our old coordinates, let's say x1, x2, down to xn, and that obviously is going to be also a member of n-dimensional R space. And let's assume that fx of x is the multivariate density, joint density of the variables xk, and similarly for fu. So similarly for fu. Then fu will be equal to fxx times the absolute value of the determinant of jg inverse, where u is equal to g inverse of x, right? Where u and x are vectors, and this Jacobian matrix is equal to partial, let's do it in gray, stay consistent. So partial x1, partial u1, all the way down to partial x1, partial un, and then that's going to continue all the way down to partial xn, partial u1, all the way down to partial xn, partial un. Right, so that's going to be your Jacobian matrix, but pretty much the formula stays almost identical, but you can have multivariate inputs for both x and also u. Now that we have the general theorem mentioned, let's see if we can actually work through an example to demonstrate its use. For our example, let's assume that x is a uniform 0, 1 random variable, so the graph of it would look like a unit rectangle supported on 0, 1, and y is going to be a gamma random variable, parameters r equals 2 and arbitrary lambda, so you can view that as the sum of two independent and identically distributed exponential lambda distributions, and then we have x times y, which is going to be the product of a uniform and a gamma. So what type of distribution will the product of a uniform and a gamma be? You might want to pause this video and sort of see if you can figure this out on your own. Else, let's jump right into it. So first off, let's start by stating the densities of both x and y. So the density for x is going to be equal to 1 over b minus a, or 1 over 1 minus 1, which is just going to be equal to 1, so we can just write 1, where x belongs to 0 and 1, and it's going to be equal to 0 if x does not belong to that unit interval. The probability density function for y can be found by convoluting two exponentials with each other, and this is going to be equal to lambda squared y e to the minus lambda y, and that's going to be true for y greater than or equal to 0. And let's see if we can find our domain for the joint distribution between x and y. So this is going to range from where to where. So x ranges from 0 to 1, and y ranges from 0 to infinity. So what we're going to be looking at is this infinite height rectangle, right? So this is the support of fxy, right? So therefore, the joint density function fxy, xy, will be equal to 1 times fy, which is just going to be equal to fy. So it's going to be lambda squared times y e to the minus lambda y, and that's going to be true for x belonging to closed interval 0, 1, and also if y is greater than or equal to 0. So that's our joint density function between x and y. And now we can start working on our change of variables mechanism. So let us define u to be equal to x times y. Notice that we're going from a two-dimensional input to a one-dimensional output, but technically speaking, you could go to a new probability density function uv if you wanted to, right? But we're not going to. So we have a couple choices that we could do. We could choose v to be equal to x, or you could choose v to be equal to y. I'm going to choose v to be equal to y, but you could choose v to be equal to x and still get the same exact answer. So what am I going to do? I'm going to solve this first equation for x, and I'm going to have x is equal to u over y, and v equals y. If I solve that equation for y, I'm going to have y is equal to v. So I have these two statements, and I need these two statements because I need to find the partial derivative of x with respect to u, the partial derivative of y with respect to u, the partial derivative of x with respect to v, and the partial derivative of y with respect to v as well to get that inverse transformation. Right? So the Jacobian of our inverse transformation, again, if you don't remember, is xu, xv, yu, yv. Right? So what will that be? So the Jacobian of our inverse will be equal to, the partial of x with respect to u, so 1 over y is our constant, so we're going to have 1 over y. The partial of x with respect to v, where there's no v's in it, and y doesn't have any u's in it, but the derivative of v with respect to v is 1, so let's just write 1 there. So that means the determinant of jg inverse will be equal to 1 over y in its absolute value, needing anything around it, since y is always positive. All right, so there is our Jacobian for our transformation, the determinant of the Jacobian. So therefore, we have the joint density function between u and v. Let's just recall the formal statement is xy times xy times the absolute value of the Jacobian's inverse. Let's write it. Sometimes people just write j as the determinant, but it really doesn't matter as long as you know what's going on. So that's the general change of variables formula, multivariate version. So it's going to be equal to what? So notice that I only want u and v in this statement. So how have I re-represented x? Well, x is just going to be equal to u over v. So it's going to be equal to fxy u over v. And y has now been renamed to be equal to v times 1 over y. So this is going to be equal to what? So this will be lambda squared y e to the minus lambda y times 1 over y. And then keep in mind 1 over y is just the same as saying v, so I can actually just write that as v, and notice that our v's will cancel here, and then we're just left with our probability density function, f uv will be equal to lambda squared e to the minus lambda v. Okay, so there's our probability density function. Now we just need to make sure that everything is fine for this. So keep in mind, 0 is less than or equal to x is less than or equal to 1, which means that 0 is less than or equal to u over y, and that's less than or equal to 1. So when I have this, I'm going to have 0 is less than or equal to u is less than or equal to y, and y is less than infinity. And why do I care about this? Because keep in mind, I have the density function for u in v, but I do know the density function for v because v is just y in disguise. So this is actually equal to f uy, and that's going to be equal to lambda squared e to the minus lambda y. But where does y range from? Well, y ranges from u to infinity, not 0 to infinity. And that is very, very important because change of variables also takes into account the domain for which we're integrating over, right? So these two components must be considered simultaneously. All right? So now I need the density function for u, so how can I obtain it? Well, I can obtain the marginal density function for u by integrating over the domain of y for the joint probability density function. That's just law of total probability. So therefore, f of u will be able to be obtained by integrating over the domain of y, and y ranges from u to infinity, so we're going to have u to infinity of lambda squared e to the minus lambda y dy. Now we can do some basic calculus. So we're going to have lambda squared times the integral from u to infinity of e to the minus lambda y dy. Lambda, again, is just a number, so this is just some inverse chain rule. So I'm just going to have lambda squared times 1 over lambda times e to the minus lambda y. And then we're going to have y is going to go to infinity, and then y is going to go to u. So as y goes to infinity, this goes to 0, and as y goes to u, it goes to minus lambda u. So we're going to have 0 minus thing, and that minus is going to revert it. So we're going to have lambda squared times e to the minus lambda u. And this is fu with respect to u. All right? So you should be able to verify that u ranges from 0 to infinity here. So therefore, this is our probability density function for u. Oh, notice, wait a minute, that lambda cancels with that, so we actually should only have 1 lambda. So what probability density function does this look like? You should see that this is indeed an exponential random variable with parameter lambda. So that's actually very neat. So what we have here is a uniform 0, 1 multiplied by a gamma to lambda came out to an exponential lambda distribution. Isn't that fascinating, right? Uniform times gamma equals exponential. It's kind of odd, right? It's actually kind of beautiful, at least to me. Anyway, that's how you actually do the change of variable transformation for probability densities for both 1 variable transformations and also 2 transformations, 2 variable transformations. And you could also do 3 variable, 4 variable, or multiple variable output transformation, for example, uv, where v is not just x or y, but v is just some completely new variable as well. So I hope you enjoyed this video, and I'll see you in the next one. Take care.